Hello and welcome to day 20 of this Advent of Code 2022. Let's read the statement for today's puzzle. Okay, we have a list of numbers. Let's copy the input. So we are going to edit the input for today. There we are. It's a list of numbers. Let's write it. Let's edit 20.py. And let's read what this is about. So this is an encrypted file where you do some mixing. Okay. For example, to move one, so to mix the file, move each number forward or backward in the file number of positions equal to the value of the number being moved. Okay, the list is circular. Okay, so we need to move one. So if we list the example, we see this is the initial arrangement, and one moves up forward one position. Okay. Two moves between -3 and 3. So 2 moves two positions forward. Okay, I think we're going to read the example too. Edit 20.x. I'm going to make the font a little bit larger. We should be able to solve this problem with few lines, I think. So I think we're going to use from collections import deck. I think we're going to use a deck, a double-ended queue. So we have quick inserts and removals of elements. We'll see if that's what we do in the end. And let's read the numbers. So let's call it L for now. And this is a list, or we can map to integer line for line in open 20.x. So instead of this is like a list. We print L. Okay, generator expression. We are missing a parenthesis. Sorry, instead of this, we can just... Sorry, what am I doing? I don't even know what I'm doing. Okay. Read split lines. So now we have to edit this 20.x. Let's edit this 20.x, remove the last line, and run it. Okay, so we have this list. Instead of a list, we could make it a deck, which would have the same elements. And now, what we have to do... Okay, what is the sum of the three numbers that you form from growth coordinates? And here it says that this is taking the 1000, 2000, 3000 numbers. Okay, so let's say what we want to do is P1 equals L 1000. Let's have an N equals len of L, just for... So it would be this, the sum. Yeah, so this is L. We could just sum N len of L, so we can maybe forget about this. For N, or for I in 1000, 2000, 3000. So this is the result. Of course, now we haven't listed these values yet. So what we want to do now is, this is going to be also part 1. So we need to move all of these elements. So how are we going to do it? Well, the first thing I think we could do, we could maybe have this as a list. And let's call this original. And then let's have this deck of the list. And one important thing is that we have to move them in the order they originally appear. So one thing we could do is enumerate this map. So we have this 0, 1, 1, 2, 2, minus 3, 3. So we keep track of which one we want to edit, right? So let's call it L so everything works. Okay, so, and here instead of summing this, we're going to list the deck and take the second element, which is 1. So now what we want to do is move all elements, right? So what we are going to do is for x in L, let's print this x. So what we want to do is let's find deck.index x. So where is this position? Okay, it's 0, 1, 2, 3, 4, 5, 6. That's right. And we want to move it. So we are going to say I equals this. Then we can remove it. So we would do, or maybe we can add it first. So we would do d.insert, in which position I plus x 1. So this is the value of x. In this position, we insert x. And then d.remove x. Does this work? Let's print d and let's break. So here we have this initially, and then we want to move 0 forward 1 position. So let's print the I and the I plus x1. So basically we're inserting this in position 1, but position 1 is not enough. I think we have to go plus 1. So now 0, 1, so 2, 1, this is what we expected. Let's print this every time. So now we have 1, 2, minus 3, 2, 1, and then it is 1, minus 3, 2, 1, minus 3, 2, 3, minus 2, and then minus 2. So in the end, we have 1, 2, minus 2. Okay, this is wrong. So if this is negative, so instead of this, let's print for how are we going to print this? Let's print dot join string of d of x1 for x in d. What is the problem here? Okay. So this is two minus 3, 0, 4. Then minus 3 moves between minus 2 and 0. Okay, this is wrong. So minus 3 needs to go back. But going back is minus 1, and minus 1 is not what we want to do. if I is positive, I plus equal 1. Let's see if that is right, if that is what we want. So here we would have x1. So let's print this message. So it will be x1 moves to position I. So here it is. -3 moves to position 2. Is that right? Let's print. Okay, so now -3 moves between -2 and 0. Again, this is not enough. So maybe else I minus equal 1. So 1 moves to position 1. 2 moves to position... Think... One minus 3, 2, 3, minus 2, 0, 4. That is right. 1, 2, 3, minus 2, minus 3. This is not good. So -3 needs to go 1, 2, 3. And -3 is in index, so -3 moves to position 2. That is not right. Oh, wait. I plus equal x1. Okay. So now this is minus blah, blah, blah. Now this is right. 1, 2, no. Now 1, 2, minus 2, minus 3, 0, 3, 4. That is right. 1, 2, minus 2 needs to move here between 4 and 1. Why? Oh, because -2 is here. So -2 is here. And it goes, so it is in position 0, 1, 2. It is in 2. It goes to position 0. 0 minus 1. Oh my god, this is a bit tricky. This is a bit tricky. Maybe one thing we could do is we could remove the number before we do the moving, right? And another thing we could do is we could rotate this deck. So if we rotate this deck, rotate, it might help, but we don't have it. We don't have it clear. So basically, let's try to think instead of just trying to hack the solution. So one thing we could do is you take the index and you remove this from the deck. So let's remove it already. So if the index is, let's say, this one here, 0, 1, 2, minus 3, it needs to go 1, 2, and 3. Negative. One way we can do this, so minus 3, well, when are we moving the minus 3? Here. Here. This is 1, so it is 1, 0. So 1, 2, 3. So when it is negative, it is inserted in the minus 2. So 1 minus 3, it is minus 2. So if it is negative, that is right. If it is positive, so the index, if it is positive, so if it is here in 1, I think now this might work because we removed before. So 2, 1, that is right. Now 2 moves 2 forward, this is right. Then minus 3 moves before 3, 0, and 4, that is right. Now 3 moves between 0 and 4, that is right. Now minus 2 moves between 4 and 1. Here the problem, we're putting it in the right position, but we are not putting it in the end, but in the beginning. So minus 2 is in position 2, and it needs to go to the end. So why does it have to go to the end? Because I don't know why, but that is a bit of an edge case. I don't know if here there's some explanation. For example, to move 1, blah, blah, blah. To move in a sequence like this, the moves position backward, wrapping around. The number should be moved in the order they originally appeared, blah, blah, blah. So the only issue we have is that if we have to move it to position 0, we want to move it in the end. So let's say if I equals 0, I equals len of L. Let's see if this works now. So now minus 2 is added to the end. 1, 2, minus 3, 0, 3, 4, minus 2. 1, 2, minus 3. What is 4? Okay, 4 got out of scope because L if I larger than len of L, we have to do this. So now 4 plus 1. Is that possible? We want to do? No. Minus 4. No, sorry. I equals I plus 1. I plus 1 modulo len. Is that right? Well, that is right, but this is a bit of a hacking solution, so I'm not sure if this is right. What happens if we run it with the input? I don't have much confidence that this is going to work. It's also not the fastest solution ever. Okay, this is the solution. I'm going to submit it. Just, okay. The full input data, blah, blah, blah. Okay, this is definitely wrong. What does the example say? I also, it says it's a 1, but that is not right. So the 1000s after the value 0. Oh, after the value 0. Okay, so I didn't realize this. So if we're wrapping out value 0, we can rotate this as much as we want. So I think the easy thing to do is to rotate this and then apply the change. anyway. So so 0 equals d dot index of 0. So this is I plus 0. Well, 0 L dot index next I for I x in enumerate deck if x equals 0, something like that. 3. Okay, we got a 3, which is, you know, something different, which is what you expect. So maybe, let's see if this is right. No, too high. So we need to think a little bit more about this. Let's think about this better. So the important thing is that 0 stays in the same place. So what we can do, let's open a terminal and let's open this deck from collections import deck. D equals deck of 1, 2, 3, 3, 4, 5. Okay, so if we rotate 1, what happens? We move it 1 to the left. So if we rotate -1, what happens? Okay, we are back. So if we want to move number 3, so index 2, d dot rotate -2, we'll just put it in front. So one thing we could do is rotate this. So we could say d dot rotate d dot index x. So now, after doing this, we have an element we want to move is in position 0, right? That is what we have accomplished by doing this rotation. Okay, let's print now. We want to d dot remove x, so we remove it. Okay, and now if it is positive, if xi is larger, x1 is larger than 0, then we insert it. So if it is 0, we insert it in the same place. If it is 1, we need to insert it 1 ahead. So d dot insert in position x1 x. Now, if this is larger or equal, else this is negative, what do we want to do? So if we have -2 and we have put -2 in the beginning, where we want to put it, we want to put it between 4 and 1. So this is going to be in the beginning. 4 and 1 are going to be the last two. No, sorry, the last are going to be, so the last are going to be, we have -2, -3, 0, 3, 4, 1, 2, -0. So we want to move -2, 2 to the left. Sorry, this is wrong. I am copying this here. Sorry, this here. So we're going to have -2, -3, 0, 3, 4, 1, and 2. We're going to remove the first element, this -2. And if we insert it in -2, this is going to be -1, -2. And that is going to be the right thing to do. So I think that is what we want. And this I, we can forget about this, and we can forget about this. And let's see if this makes any sense. So -2, 1, 2, -3, 4, 0, 3. So now this is right. This is right. Let's see what happens if we do this with the input. If we get this 16,000 that we were getting. Now this is different. So let's. Okay, too low. I don't like it that this is too low. Why is this too low? Because now we're doing the example right, and I think the problem is pretty clear. Let's print for I in all of this. Let's see if we're getting really the exact number. So we are going to print this. For the example. Okay, 4 minus 3, 2. 4 minus 3, 2. So this is right. So we are summing the right indices. So the numbers should be moved in the order they originally appear in the encrypted files. Numbers moving around during the mixing process do not change the order in which the numbers are moved. Okay. For example, to move the 1 in a sequence like this, we need to move it ahead 1. So in the case of positive numbers, I think it's clear that we are doing it right. This remove, we could also say pop left. That's what we are doing. We're just popping left. Okay, this is the we have the same element. So we rotate. Element we want to move is in position 0. So we move this number to the index. What happens if index is 0? Well, it will be, we will not rotate it, right? If we d dot rotate 0, it stays the same. If we do d dot rotate 4, sorry, -4, what happens is that the last element goes to the beginning. So the index, now with this, the first element gets to the beginning. We remove the first element and we insert this element to the index of whatever it says here. So if this is okay, the problem we could have is that the length of the print the length of L, the max of L, and the min of L. Let's say here numbers. So x1 for x in L. Okay. Okay, now that is a problem. So these numbers don't add up. We are inserting farther away than we can. So we need to insert this and do this modulo length of L. Otherwise, we are not getting the right solution. The other problem we have, okay, is that we could have negative. modulus that we need to do, and that may also be something difficult. So I think it is clear that the problem we have is with this wrapping around. So what happens if instead of -1, I think the problem is that you could the fact that we remove this element before doing any wrapping, before doing the modulo, well, no, but we do the length of L, so we are taking into account the whole of the length. But what if we had to move 10,000? Would it stay in the same place or not? I don't think this is clear from the statement. To move the -2 in a sequence like this, 2 positions backwards, wrapping around. The numbers should be moved in order of they originally appear in the encrypted file. Numbers moving around during the mixing process do not change the order in which. So we have seen that you can move 9,990 forward in a list of 5,000. So we put this in the beginning. So one thing we could do is plus 10 times the length of L. Now we have a different result or no, or we have the same result. I think we already submitted this. Not 100% sure, but I think we already submitted this. If we do the length of len, we do the length of D, then we're going to get a different result for sure. That's not the right answer. 5 minutes. Now I have to wait for 5 minutes. So what does it mean to move? I'm a bit stuck, honestly. I'm a bit stuck right now. Because this looks pretty okay. You remove this number, pop left. What happens if you... Sorry. If you remove, did it remove 4? Does that return anything? No. Okay, let's do something. So if I do d dot insert in position 0, 1, 2, 3, 4, in position 3, I insert a 9, what happens? And if I do it in position 5, what happens? It inserts in the end. But if I put a 0, so this could be this plus 1, 2. So the problem with wrapping around so you have D. So now 0, 1, 2, 3, 4, 5. If you insert in 0, 1, 2, 3, 4, 5, 6, 7 a 3 or a 999, what happens? 0, 1, 2, 3, 4, 5, 6, 7, 8. So it just puts it in the end, right? So if so you want to skip 7. So you say remove 1 and you skip 0, 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7, 8. Oh, this is pretty bad. Know how to do this. I don't really know how to do this. I know the solution is just like +1, -1, this kind of things. But one thing I'm not sure we tested. Okay, we got the gold star. So when we are moving around, we need to do the modulo. The modulo we need to do is the remainder of the length of the queue after removing this first element, right? So one thing we could do, probably we could let's check the second part and then we can modify. So the part 2, you need to mix the list 10 times. So we could maybe say def mix, given a list, we do this deck of the list. Even the list could be enumerate L, so we don't have this. And here what we would do is mix L, we return D, so we can say D equals mix. This does not work. What are we printing here? So D is enumerate L. Well, we can forget about this. Is not in deck. So this list print L. This is just a list. We can work with the example to do this refactoring. So here, rotate index X. What is this D now? We have this enumeration, so this is right. And now we have to find the index for X in L. So here we could say enumerate okay, so and this is the input. So this is what we really have as a solution. We could assert p1 equals this. We're ready to go. So now part 2. So in part 2, we need to mix this 10 times. 10 times. So how are we going to do this? You know, maybe the deck, we could have it here. So well, when you do it 10 times, the second time you have to do it in the same order, right? So let's see how we can do this 10 times easily. So this is not going to work because we're modifying the list. So rotate, pop left, insert. Here, let's say def. What is the calculation you need to do? What is this called? Let's say the solution. Solution giving a deck is this. Return this. So this is the P1 is the solution of this deck. This is P2. Okay, so now what is 0? So 0 is up here. Okay, so now instead of mixing it once, we need to mix it 10 times, right? So what we could do, how do we mix it 10 times? So we need to mix it 9 more times. So one thing we could do is for this in range 9, what we could do is have a list. New list is x1 for x in deck, and then deck is mix the new list. Okay, now print P2. And the other thing we need to do is this. You need to first multiply each number by this. Okay, so now we cannot do this 10 times. So we do this 10 times. And we have to multiply this. So L equals n times this for n in L. So we have multiplied this L. We have this negative number. Let's submit it. No. Okay, so what are we doing? We could also test the example, which would make more sense. So now let's print P2. So now P2, okay, P1, also the assertion doesn't work, but it needs to be 3. Okay, now we have this number which is wrong. So what are we doing wrong now? We have to mix it. We have to mix it. After one round of mixing, let's print D. So this is 0 minus 259, 3, 2, blah, 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 8, 1, blah, blah, blah. That is right. After 2 rounds of mixing, we have 0. Now this is wrong, because I think we're not doing this right. So I guess the second time we mix it, we need to do it in the same order. So are we always putting the 0? So the initial arrangement is this one, and then the 0 stays in the same place. So I guess I don't know what I'm doing. That's what I don't know. So 0. So the second time, after the 0, we have the -2, blah, blah, blah. So the order in which the numbers are mixed does not change during mixing. Okay, they have to be moved in the original order. So the original order, original equals L this. So it has to be mixed in the original. 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 So the original is this. Deck is not, this value is not in deck. Okay, so for X, enumerate the original. The deck is going to be original dot index X, comma X for X in L. Okay. Okay, now that is right. So this worked. Now we are going to refactor this heavily after this. So now let's try with the input. Okay, number is not in deck. What? But this is a very small number. Wait, this assertion doesn't look right. Mix LL. I don't know. Can we forget about this? No, this is not right. Oh, wait. Let's copy this because maybe we are just modifying this. Okay. So let's try to refactor this a little bit to get the second part right. I got somehow the example working, but now the input is not working. Okay, this assertion is error is wrong. Now this is right. So what is going on here? The order instead of doing this, let's enumerate this map. So we have the list is already enumerated. So now we want to mix this list, but we copy it. Oh no, we don't copy it. We just send it. So this deck we just make a deck of this list. So instead of enumerating this list, original equals a copy of this list. So if we enumerate original, we rotate this index, pop left, blah, blah, blah. And we have this deck. Instead of having this deck, we could have deck equals deck of list. So if we here we get a deck, we just mix it and return this same deck. What is good about this is that we're creating a deck of this list. Let's call this, we're going to call it list. So we can take this L, and now we have this. Let's see if this works. Okay, this is not in deck because we're enumerating this, which we don't need. Something got wrong. Okay, so we have to mix this in this way. So first we need to mix it in the order of that we read it. So we have this enumeration, we have this list, blah, blah, blah. So for each element, we find this in the deck. So the deck is a mix of this, and we have the solution of this D. So this somehow gets in an infinite loop, which I don't understand why. Print P1. Okay, it prints a 3. Okay, so let's see now the second part. Maybe there's some issue with the second part. Okay, so the L, we are modifying it for N in L. Original, let's forget about it. So we are going to mix the deck of, so let's say dx a deck of L. This is not right because this is, oh, this is multiplying a list or something like that. So this is going to be for I n in L. This is going to be I n times this. So now we're modifying the original list. We're creating a deck of this list. And then what we do is we just mix it. We mix it and we apply it. So we are mixing it 10 times and then we print the solution. So this is right for the example. Let's try it for the input. Assertion error. So this assertion is wrong, of course. Now it's thinking, and now we got the solution. Let's see. And we got the gold star. Okay, that was tough, but we did it. So let's assert P2 equals this value. It was a bit tough to find the solution for this problem. Took more than expected, but I think the solution we found is pretty good. So first, the 0. One thing we could do is enumerate the list. If we enumerate the list, we can remove this enumerate from here. And what should we do then? Well, deck of enumerate the list. This is going to be the deck of enumerate the list. And this 0 is just L.index 0. Is that right? Deck L sol D enumerate for L. This is going to be just n times blah 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 for n in this. Okay, part 1 is already not working. Enumerate L. Print D. Okay. Enumerate L. So I don't know what the issue is. Well, I know what the issue is. This is not right. So this is not L.index. So the 0 is the D.index of L.index 0, 0. Now that is right. Okay, so when we do this, we can probably simplify this a little bit. P1 equals that, so we can do that in one line. And another thing we can do is, well, we could put this in a single line for sure. And now we're just mixing this 10 times. What did we do now? This is not, oh, because we need to modify the L. The L is used inside here, so we need to modify it. And P2 is the solution of this deck. So solution is this. Here we rotate, we pop left, and we do this. Could we just remove D dot? So could we remove X? And have, I mean, could we simplify this? Instead of rotate and pop left, could we do D dot remove? So could we do I equals D dot index X and then D dot remove? But it's not better. So it's nice that we rotate, pop left, and insert. Do this all this many times and return D. Instead of return D, we could just, well, if we did not return D, we could just do the mix without assigning it, but I think it is fine if we do it. We could even not return it, but if we don't return it, we cannot do this, call this solution. So we will call it like this. So this is a deck, so we mix this solution D. No, not this. No, this is, but this is. So we do D like this. D is deck, and we do the mix D, solution D, right? I think it's better to return it and be done with it. So we have this in a single line. We do this, we return it, solution, part 1, part 2. We just modify this list. We have the deck, create the deck, mix it 10 times, and solve it. Well, we can refactor this a little bit, but the solution is pretty efficient, pretty fast, and works. Pop left, insert. And then we are summing this D I plus 0 modulo length. So we could also say, D dot rotate minus this. If we did this, we would just say I. That's right. So we could say di1 for I in blah, blah, blah. So we could say return D1 plus D1 plus D1, which is shorter and works. And here we just need to rotate this. So we rotate this, and this is the L dot index 0, 0. So we rotate it to put the 0 in the first position, and then we just take the elements 1000, 2000, and 3000. That's another way to do this. We could modify solution to solve to solution. So we calculate this number just with a solution, and then we have this enumerate. We could have the enumerate in the beginning. So if we did this, what would we save? We can remove this enumerate here. We can remove this enumerate here. So we are removing two enumerates, and here we need to add one. So this is I blah 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 for in in L. That's what we modified, but here also L.index, we don't find it. So I think I liked it better to remove the enumerate from the beginning and keep it. And now this, we do this 10 times. We could also, you know, mix D. This is done 10 times. So we create the deck, mix it 10 times, and we are done. Okay, so can we improve this in any way? We just rotate this. And take this. So So we have the mix function, which takes a deck and returns a deck. It is not very clear the fact that we need to return a deck, but if we use the list, we would need to make a deck of this list, which is not ideal. So this deck, we cannot just enumerate it inside here, because when we do this many times, we need to. So I think it makes sense for us to have this deck that has this, it just takes a deck, returns a deck. I think that makes sense. We could remove this returning a deck. If we removed it, so we could add one new line here. So this would be deck of enumerate L. We mix D, and then P1 is the solution of D, right? We did this. Here we can remove this equal. So we just have this. Now the other thing is that maybe we could say numbers. Well, what are these numbers exactly? Apparently coordinates, right? So we could call it, you know, coordinates. These are coordinates. And here we could have a parameter L. So we mix this with coordinates, and we mix this with coordinates. Coordinates. Is that right? Okay, L is not defined. Coordinates. Where is L being used? L coordinates. Coordinates using global variables is generally not advised, right? So when we do this mix, here we have the coordinates are these, do the enumeration, blah, blah, blah. We removed the global variable, but we had to add it in many places. So I think I'm going to backtrack and just keep it like we had it. So now this is working. So one thing we could do here, we could also add steps. Let's say for in steps, we do this. We don't need to return D, and steps could be equal 1 by default, and could be, you know, like this, mixed D10. Let's see if this works. Instead of steps, this is a range. So now this works. So if now we have these steps, we can put this here, simplify this code a little bit. Okay, we get an assertion error. Why do we get an assertion error? Well, because we're not. Let's return the deck. So now we can say mix this, and here we do the same, mix this, right? Let's see if that works. Okay, so now we have this part one. It's just, we could also say P1 is the solution of this. So now we have a one-liner, it works. And regarding the second part, well, this is the same, right? P2 is the solution of this. We could also say have the solution as part of the, you know, instead of having two functions, we could have this as a simple, as a single function. So if we do this and call this, you know, solve, this is solve, and this is solve. So now this is even shorter. So now we're mixing and returning. So this solve is just this. So now L, we could enumerate it here, right? So we don't have to do it. No. I think what we need to do is enumerate this outside. If I'm or am I wrong? Maybe I'm wrong. Okay, wait. Oh, because here we have this L, but of course this L, if we took L as a list, we should call it deck. Wait, we have to put the L here. So here this would be deck L, deck L. That works, I guess. No, it doesn't. Oh, well, because we have the enumeration inside here. So now this should work. Now we're using the L from inside, not the global one. So that makes sense. Of course, the difference is that we want a deck that uses enumerate, and here we're just using L. So this L is used inside here. What for? Okay, we're enumerating this list. So if we enumerate inside here, we would remove 1 enumerate, 2 enumerate, and 3 enumerates. So if we enumerate this, we can remove this L, this L, and this L, and here this index would not work. Instead of the index of 0, this would be next I for I underscore or I x in enumerate, oh sorry, in L if x equals 0, something like that. And this is not working. This is not working. Okay, so this is working. No, this is not working, sorry. This thing is not right. We need to rotate the index of this I for ix in, oh, enumerate, we already have it. We already have the enumerate. Do we have this? Okay, this is never getting called, so probably we'll have some other issue. Well, now I lost the undo. So what we had here is L.index 0, that's what we had, and the L was this, and here we had enumerate L, enumerate L, and sorry, here enumerate L and enumerate L. So this is not in deck. What is the issue now? What is the issue? L.index 0. Okay. Okay, now this is working. So basically, to summarize again, what we're doing is we're solving this by adding this deck to enumerate L, deck enumerate L. Of course, now we don't need to return this deck. So we don't need this deck as a so this is the deck of enumerate L. So now we just can say solve L, solve L10. Okay, this is even simpler. We are only using the deck inside of the list. And of course, we can also do this list comprehension inside of this parameter. So now we have this list comprehension here for n in L. So here we could also use this, coordinates. We could call that. So we have the coordinates here and the coordinates here. So part 1 and part 2 are very simple. This here we are just doing solve coordinates, solve the modification of these coordinates, so this multiplier and 10 steps. And here we have a list, which we only used in a couple places. So we have this deck, which is the enumeration of a list, of the list. You know, read input. We could put it here too. Or we could put it up. Maybe up is fine. So we do for each step, we have this deck initially, which has this enumeration. And then for each enumeration of the L, we do these steps. We rotate, we pop left, and we insert. One thing we could do, maybe there is one way of doing this all at once, which would be, maybe not. So the index, or I, could be the d.index of x. So this is then we could d.remove I, and we could say d.insert I plus x1 modulo len d x. I wonder if this works. No. We remove x. If this works, this will be interesting. Okay, so these are two ways of doing exactly the same thing. See? Here we do the rotation, and here we just take the index, remove, and insert here. I think this one is simpler, because we don't need to rotate. We just add. This is more similar to what the statement says. We just add to whatever index we have here. So what we could do, I wonder if we can do this in a single line, you know? So this would be, we take the index of x, we remove it, and then we insert it back. So it's clear that we need to remove it. d.index. Remove doesn't return any index or anything, as far as I know. I think I already tested this. From collections, import deck. So deck d equals deck of, 1, 2, 3. d.remove 2. Doesn't return an index or anything. The index 3, we have the index. So we really cannot reduce this line as far as I can tell. So what we are doing, if we remove, of course we cannot take the index later. So one thing we could do, I don't think there is much more we can do. So we can take the index, we remove it, and then we do this. So this part, of course we could call it index. Index should work. I think I will keep this one. I will update this with this solution. It's a bit more verbose, but it makes more sense, because instead of rotating and pop left, we just take this index, remove this one. So d.remove, it's interesting that it takes a value. What else do we have here? Pop left, remove. reverse, rotate, extend left, count, copy, clear, append left. So we don't have any way of removing an index. So I think I will keep it. I will do it this way. And then this rotate, we could also do the same. So instead of rotate, we could probably, take the index. So let's try to do an alternative. So this would be for I in this list. Well, maybe, or in, well, let's do 1 E3, 2 E3, 3 E3. It's a simple way of, we save 3 characters, right? Well, maybe it's an exaggeration. We should just put this here. This way it is more understandable. So we would return the sum of what? Of d dot index of 0. So the index of this guy here plus I, and of course this I needs to be wrapped around, otherwise it doesn't work. So this works. But maybe it is not the easiest. If we remove this, it's definitely not gonna work. It might work, but it could fail if I understand this correctly, because we're adding this to the index. So it could be so this is the index of 0, so where the 0 is located. Okay, we'll keep it. So we have, on one side we use rotate, on the other we don't. It's fine. So I think it's difficult to make it, shorter than this. We read the coordinates. We solve the problem by building a deck. For each step, we move these numbers in the order of the original list. So we could also change this to coordinates, coordinates, but I think L, I don't know. I like L. It's just a list, whatever. LD. So we create the deck. For each step, we iterate through the list of the numbers of the list in order. This X, why X? This is an integer, so let's call it N. Well, it's not an N. It's not an N exactly. It is a pair. So maybe, I don't know, let's call it pair. Let's call it pair P. Not the best name in the world. We rotate this to put the 0 in the beginning of the deck, and then we take these indexes. We solve this directly, and we solve it multiplying its number by this. I guess this is a prime number, probably. And I don't know if it's a prime number. Let's check if this is a prime number, right? Would be interesting to know. So we can factor this number. Okay, yeah, it's a prime number. So that was fun to check. So here we are. Let's write about the lessons we learned today. So first of all, heavy use of deck. We used pop left, we used rotate, We used index, we used remove, we used insert. So deck is a very good data structure for removing the leftmost element, rotating, because this is just updating a couple pointers. Getting the index is definitely not fast. This must be linear. Removing must be linear. Inserting must be linear. But still, it is the right data structure for this problem. What else did we do? Well, we used enumerate to pair each n with its index, right? So we had 0 whatever, 1 so 1, etc. And that was very helpful for keeping track of where the original numbers were. So if we need to modify the third number in the list, we have paired it with a 3 or with a 2 in the deck, and it is fine. It is easy to find, right? Well, we did some modular arithmetics. So we need to wrap around the list. So the way of doing it is n plus y modulo the length of the deck or the length of the list. So this way we wrap around, and when we get to the end, we can go back. It's interesting that works for negative values. So it works out of the box for negative values. There's no special case that we need to take care about. And then what else? Well, we used some list comprehension, very, very simple list comprehension, and so on. So, and then finally, I would say one important thing is that we, it is possible to get very short solutions. So in this case, we started with a more or less verbose solution, and I'm pretty sure there's some way to improve this. I'm very sure there's always ways to improve this, but I think this is a very good example in which, with very few lines and a single solve function which we can reuse for part 1 and for part 2, we were able to solve this problem. And that is good to know and to keep in mind, because when you're solving one of these problems, many times, well, you can see my videos are very long, so many times you could end early. And there is this quote in computer science that working code is not enough, right? So it's not enough to solve the problem. You need to leave a good code. You need to refactor it. You need to simplify it. You need to deeply understand the problem, and so on. So probably, for sure, there is a better way of solving this, but I'm pretty happy with the solution and how brief it was in the end. I hope you enjoyed this video. Let's see you tomorrow.